Welcome back to the lecture on quantum chemistry. We were discussing about one-dimensional simple harmonic oscillator. In the last class, I just introduced the quantum mechanical approach of one-dimensional simple harmonic oscillator, where I gave these expressions. This is the expression for Hamiltonian operator, and this is kinetic energy part, and this is potential energy. Then the equation that we have to solve is H psi equal to E psi, called the Schrodinger equation. In this derivation, I have introduced two constants, beta and alpha square. Okay, beta is nothing but 2 mu E by h bar square, and alpha square is k mu by h bar square. Okay, then I have converted the variable x into a dimensionless variable q. Okay, then after substituting that q, right, the second order differential equation get modified, and finally we got this expression to solve. Okay, so if you solve this equation, right, we'll get the solution for the Schrodinger equation. Okay, right. So how to solve this equation? So what I'm going to do, first let me find the asymptotic solutions. Asymptotic solution. Asymptotic solution means what will be the nature of the wave function when the variable approaches plus infinity or minus infinity, right? See, we know very well, as x approaches plus infinity or minus infinity, okay, q also will approach plus infinity or minus infinity, right? So when q approaches plus infinity or minus infinity, what will happen to the function? We all know that for a well-behaved wave function, the function should vanish when the variable approaches plus infinity or minus infinity. Okay, so we'll check whether what kind of or what form of the wave function will appear like when q approaches, or in what way the wave function will appear when q approaches plus infinity or minus infinity, so that the wave function should vanish. Okay, yeah. So let me find the asymptotic solution first. So what to do? When q approaches plus infinity or minus infinity, that is when q approaches very large value, okay, this equation can be reduced to d square psi by dq square. If you compare lambda and q square, when q square approaches very large value, lambda is negligible, so you neglect lambda, so I can write minus q square psi equal to 0. Okay, when q approaches very large value, plus infinity or minus infinity, right, then lambda compared to q square, lambda value is negligible, so you can neglect. Therefore, we can write simply minus q square psi equal to 0. Now, what is the solution for this? Right, you can find the solution by solving this, or we can also do in this manner. Say, for example, let me introduce, or let me give the solution as psi equal to e power minus q square by 2, and another solution psi equal to e power plus q square by 2. Actually, both these solutions, okay, will be valid for this differential equation. Okay, yeah, you can also check it. How? You just differentiate this 2 times and substitute in this equation. Okay, whether this equation valid or not, you can check. Yes, how to do that? Yeah, I'll differentiate this once. D psi by dq equal to e power minus q square by 2. If you differentiate exponential term, you will get the same e power minus q square by 2. And in the power, we have minus q square by 2. If you differentiate q square, you will get minus 2q by 2. 2 cancel, so you will get minus q. Okay, this is after differentiation of psi. Now we have second derivative here, so differentiate this again. D square psi by dq square. Yeah. d square psi by dq square can be given as, so you take minus as common here. Okay, so we have e power minus q square by 2 and q. We will apply UV method. So first keep e power minus q square by 2 as such. Differentiate q. If you differentiate q, you will get 1. Then plus, keep q as such. Differentiate e power minus q square by 2. You will get e power minus q square by 2. Then minus q. Right? Because if you differentiate e power minus q square by 2, you will get e power minus q square by 2. And the power on differentiation will give minus q. Okay. So, if I take e power minus q square as common, I will get minus. I will take e power minus q square by 2 as common. So, I will get plus 1 here, and here q into q square, so I will get minus q square. Or if I bring minus sign inside, I will get q square minus 1 into e power minus q square by 2. Okay. When q approaches very large value, okay, 1 is negligible compared to q square. So we can also write this as q square into e power minus, this is nothing but psi. Okay, this is nothing but solution psi. Okay, right now if I bring it to the left hand side, what will I get? Let me write here. So d square psi by dq square minus q square psi equal to 0. So I got this equation. Okay, therefore this is a valid solution for this differential equation. Similarly, you can also show that this is also a valid solution for the differential equation. Okay, but if you analyze the two wave functions, okay, you need to identify which wave function vanish as q approaches plus infinity or minus infinity. I repeat, the two solutions are valid solution for the differential equation. Okay, but we need to identify which wave function vanishes as q approaches plus infinity or minus infinity. Okay, yeah, let me check it. Let me do it here. Yeah, so as q approaches plus infinity or minus infinity, okay, the function e power plus q square by 2, first I will take plus q square by 2, as q approaches infinity, the function e power q square by 2 will also approach infinity. That means the function diverges. Right? It is not an acceptable function. Okay, I can say simply it is not an acceptable function because the function should vanish when q approaches plus infinity or minus infinity. Okay, then similarly, as q approaches plus infinity or minus infinity, what will happen to this solution? E power minus q square by 2. Now we have minus sign in front. So when q is plus infinity or minus infinity, okay, q square is positive, but we have minus sign in front. Therefore, e power minus q square by 2 will approach 0. Okay, so this is the acceptable solution. Right? So for the differential equation, for this differential equation, two valid solutions are there, but for our problem, okay, or for the wave function to be acceptable, right, the wave function should vanish when the variable approaches plus infinity or minus infinity, right? Under this condition, right, if you analyze the two functions and this function comes out as the acceptable function. Okay, therefore, under asymptotic condition, the acceptable solution is e power minus q square by 2. See what I am trying to say? When q approaches plus infinity or minus infinity, the wave function, right, behaves like e power minus q square by 2. Okay, and this is called asymptotic solution, right? But this asymptotic solution is valid only when q is very, very large, right? What will be the nature of the wave function, right, when between minus infinity and plus infinity, or in the intermediate values? Okay, so for complete solution, I can write complete solution can be written as psi of q equal to, complete solution can be given like this. That is, it consists of an asymptotic part e power minus q square by 2 asymptotic solution, and asymptotic solution will take care of the wave function at large value of q, at when q approaches plus infinity or minus infinity, right? In the intermediate values, we need some other function that should take care of the wave function in the intermediate ranges. Okay, let me take that function as h. Now what I am going to do, if the wave function consists of this part and this part, what will happen to the differential equation? Okay, we'll change the differential equation by incorporating this h. You will get a new differential equation. Okay, then we'll solve that differential equation to find the solution for h. Okay, see what I'm trying to say. So I'll take this as the complete solution. Remember, this part will take care of the solution under large value of q, and this part will take care of the solution in the intermediate values. Okay, now the question is, what is the nature of this function? To find that, what we have to do, see this equation. So this is, let me take this as equation number 1. Okay, I'm going to differentiate this psi 2 times and I'm going to substitute here. If I substitute here, I will get a new differential equation in terms of h. If you solve that differential equation, you will get the solution for h. Okay, yeah, let me do that. So what we have to do, differentiate this 2 times. So d psi by dq equal to, first I'll keep this e power minus q square by 2 term as such. We have to apply UV method. I'll keep this term as such and I'll differentiate this. If I differentiate h, I'll get dh by dq, right? Plus, then keep h as such, differentiate this, you'll get e power minus q square by 2. If I differentiate this exponential term, I'll get e power minus q square by 2. Then power, in the power we have minus q square by 2. Q square on differentiation will give 2q, 2 cancel, so I'll get simply minus q. Okay, so I can write this as e power minus q square by 2 into dh by dq, okay, plus into minus minus h into q into e power minus q square by 2. Right, now I'll do second differentiation, second derivative, d square psi by dq square. If I differentiate second time, what will happen? So again apply UV method here. So keep e power minus q square by 2 as such, differentiate this, you'll get d square h by dq square. Then keep dh by dq as such, differentiate this quantity, I'll get e power minus q square by 2 into this, on differentiation will give minus q. Okay, we have completed this. Now I'll come here, minus. Now I have 3 functions which depends on q. Okay, so we have to apply u, v, w method. So first I'll keep u and v as such, I'll differentiate this. E power minus q square by 2 on differentiation will give e power minus q square by 2 into minus q. Then minus. Now I'll keep h and e power minus q square 2 as such, h and e power minus q square by 2 as such. I'll differentiate q. Q on differentiation will give 1. Then minus, I'll keep q and e power minus q square by 2 as such, and I'll differentiate h, I'll get dh by dq. So this is the result we obtain after second differentiation. Now let me simplify this. Okay, so I'll keep the second order differential term as such, e power minus q square by 2 into d square h by dq square. Now the dh by dq term I have in 2 places, so let me combine them. So here I have minus q e power minus q square by 2 dh by dq. Here also I have minus q e power minus q dh by dq. So I have 2 terms, therefore minus 2q e power minus q square by 2 into dh by dq. So by adding these two terms, that is this term and this term, I'll get this minus 2q e power minus q square by 2 into dh by dq. Then the remaining term we have, okay, here I have minus into minus become plus hq square, h into q is q square, hq square e power minus q square by 2, and here, so let me write those terms as such. So minus into minus become plus h into q square into e power minus q square by 2. So this term goes over, and here we have minus h into e power minus q square by 2, and here we have minus q into e power minus, I'm sorry, we have completed this term already. Okay, so this is the differential equation I got, okay, after second differentiation. Now let me incorporate this in equation number 1. Okay, so what is equation number 1? First let me write equation number once, then I will substitute this. Okay, so equation number 1 is d square psi by dq square plus lambda minus 1 into h equal to 0. This is the equation number 1. Now what I am going to do, in the place of d square psi by dq square, I am going to substitute this value. So you will get e power minus q square by 2 into d square h by dq square minus 2q into e power minus q square by 2 into dh by dq, okay, plus h q square e power minus q square by 2 minus h into e power minus q square by 2. Then we have this term, that is plus lambda minus 1, and I can also separate this. Okay, let me write once. Lambda minus 1 into h. What is h? I'm sorry, this is not h. Lambda minus 1 into psi. I'm sorry. Equation 1 is lambda minus 1 into psi. And what is psi? Psi is h into e power minus q square by 2. Okay, psi is the complete solution. The complete solution is of the form h into e power minus q square by 2 equal to 0. Now, see this term. In all these terms, the term, first term, second term, all these terms has e power minus q square by 2. So, I will divide throughout by e power minus q square by 2. Therefore, this equation gets simplified as d square h by dq square minus 2q into dh by dq. And here, e power minus to cancel in all the places. I will take h as common. So if I take h as common, right, here I have q square term, okay, here I have minus 1, here I have plus lambda minus 1 equal to 0. Okay, so this is the term that we have here. Okay. I'm sorry, actually, yeah, I think I made a mistake. Let me check it out. Yeah, this is not equation 1, I made it wrong. This is lambda minus q square is there, q square. So this should be lambda minus q square. This is lambda minus q square. Yeah, I made a mistake. Sorry. Yeah, so plus q square minus q square cancel. So I'll get a new differential equation in terms of h, d square h by dq square minus 2q into dh by dq plus lambda minus 1 into h equal to 0. So now I got a new differential equation, second order differential equation in terms of h. Okay, and this equation is what we call as Hermite differential equation. Hermite differential equation is a very famous equation in mathematics, and the solutions are already available. But anyway, I am going to solve this by using power series method. Okay, to get the solution, so what is the solution of h? That's our goal. To get the solution, I am going to apply power series method. power series method. See, power series is an infinite series in which you can guess the solution as, let me guess the solution for h as h of q equal to, okay, I'll guess the solution as summation I equal to 0 to infinity. The power series solution will go up to infinity. Remember, here I is an integer. I can take value 0, 1, 2, 3, 4, etc. I is an integer. It can take value 0, 1, 2, 3, 4, etc. Okay. Then a coefficient a, I, into the function, the variable q power I. This is the usual way of defining the solution in power series method. Okay. So here, what's the meaning for this? If I put I equals 0, I'll get the coefficient a0, q power 0. Q power 0 is 1 anyway, plus I equal to, if I put I equal to 1, I'll get a1 into q power 1, then a2 into q power 2, right? Like that it goes. So this is the power series solution. We know q, we know the form of q. What we need to find out is the coefficients. If you find the coefficients, right, you will get the solution of h, or you will get the nature of h. Okay. So in power series method, we write the solution, okay, in terms of infinite series like this. In this infinite series, if you find the coefficients, right, you can say what is the nature of the function. Okay. Now, how to find the coefficients? What we have to do? Differentiate this 2 times. Okay. Substitute here and here. Okay, and check how the coefficients, right, are related by one with another. Okay. Let me take this as equation number 2. Okay. Yeah. So now what I'm going to do? I'm going to differentiate this 2 times. Let me write to the next page. So if I differentiate once, I get dh by dq equal to summation I0 to infinity, I equal to 0 to infinity. We have the coefficient ai, I keep it as such. Q power I on differentiation will give I into q power I minus 1. Right. So this is the first derivative form we get. Okay. This q power I minus 1, let me keep it as such, because in the differential equation, I have a q here. So when I multiply q with the dh by dq, right, q power 1, q power I minus 1 will become q power I automatically. So I am not going to disturb this function as this function. So let me keep it as such. Now I will do the second differentiation, d square h by dq square equal to sum of I0 to infinity. Let me keep this ai as such, I as such. Q power I minus 1 on differentiation will give I minus 1 into q power I minus 1 become minus 2. Okay. Now, if you see the second equation number 2, the second differential of h, okay, in front we don't have any q here, q or q square term, right? So what we have to do? We have to convert this q power I minus 2 into q power I. Okay, see, what I am going to do is, I am going to substitute wherever I is there, you put I plus 2. Since it is an infinite series, I to I plus 2, nothing make any difference here. Okay, so you need not worry. So what I am going to do, this is also equal to I equal to 0 to infinity. Okay, let me put in the place of I will put I plus 2. Wherever I is there, you put I plus 2. So here I have I, so I plus 2. Here in the place of I plus I, if I put I plus 2 minus 1 become I plus 1. I plus 1 into q power, in the place of I, if I put I plus 2 minus 2 cancel, I will get q power I. Okay, so this is the term I get. Now I will substitute all these things in equation number 2. Okay, if I substitute these in equation number 2, what will I get is, so in the place of d square h by dq square, I will put this sum over summation equal to 0 to infinity, the coefficient a I plus 2 into I plus 2 into I plus 1 into q power I. Okay, then second term, see in equation 2, the second term is minus 2 into q into dh by dq. We know very well dh by dq is this. So if I multiply by q power I minus 1 into q become q power I. So I'll get, 2 is there, so I'll keep the 2 as such, into summation I equal to 0 to infinity ai, the coefficient ai into I, right? Ai into I, then this q will become q power I. Okay, then the third term, which is lambda minus 1 plus lambda minus 1 into h. What is h? H is the solution, that is I equal to 0 to infinity ai into q power I equal to 0. Yeah, so for this to be valid, either qi should be 0 or the coefficient, or this coefficient should be 0. Remember, or sorry, this quantity should be 0. Listen, if qi is 0, then the function becomes 0, because we have defined the function like this. Okay, h is equal to, sorry, previous page, h is equal to a into qi. Okay, if qi is 0, then the function becomes 0. Okay, then it becomes meaningless. So qi cannot be 0. If qi cannot be 0, then the terms that are present in front of qi, that must be equal to 0. Okay, see, what I'm trying to say is that so here the coefficient is, every coefficient should become 0. Okay, sum of every coefficient should become 0. That means ai plus 2 into I plus 2 into I plus 1, this part, and here minus 2 into ai into I, this part, and here lambda minus 1 into ai. Okay, for each I value, this the sum of these coefficients, these terms should be equal to 0. Okay, only then this equation is valid, right? Or I can also write this as ai plus 2 can be written as this part, when it comes to the right hand side, we will get 2ai. Okay, I'm sorry. If it comes to the right hand side, I'll get 2ai into I. I'll keep this 2i as such. Okay, I'll take ai is common here. Ai is common, so this becomes 2i. And here we have plus lambda minus 1. So minus 1 when it comes here, it will become plus 1. Plus lambda will become minus lambda. I have taken ai is common. Divided by, we have this I plus 2 into I plus 1. Okay, yeah, let me write in the next page. So what we got here is ai plus 2 equal to 2i plus 1 minus lambda by I plus 2 into I plus 1 into ai. Okay, this is what we call as, this relation is called as recursion relation. Recursion relation. Okay, this relation is called recursion relation. It's a very, very, very important relation, because if you know one coefficient, you can find the other coefficient. What is meant by that? Suppose if I know a0, suppose, right, if I put I equal to 0, I'll get a0. If I know the coefficient a0, right, if I put a0 here, a0 means I value 0. If I put I0 here, I'll get a2, right? So that means if I know the coefficient a0, I can find the coefficient a2. Similarly, if I know the coefficient a2, I can find the coefficient. If I put a2 here, a2 means I is 2. If I is 2, I'll get ai, I is 2, 2 plus 2, 4. So I'll get the coefficient a4. If I know a4, I can get the coefficient a6, right? So and so on. So all even coefficients, right? 0, 2, 4, 6, all even coefficients can be obtained, right? if I know A0 using this relation. Similarly, if I know A1, right? If I know A1, yes, I can find all odd coefficients A3, A5, A7, right, etc. All odd coefficients can be obtained, okay, if I know the value of A1 by using this relation. And this relation is called recursion relation, which is very, very, very important. Okay, now, before going to see the actual nature of function, what will I do is, here, listen, this is very, very important. When I approaches a large number, okay, suppose if I approaches large value, okay, what will happen? If I approaches large, then this coefficient ai plus 2, I'll bring this ai to the left hand side. Ai plus 2 by ai becomes equal to, when I become very large, okay, so 2i is very, very large compared to 1 and lambda, so you can neglect 1 and lambda, so this will become roughly 2i, numerator. In the denominator, I plus 2, if you, since I is large, you can neglect 2. Since I is large, you can neglect 1 here. So I will get I, here also I into I become I square. I square, or this is equal to 2 by I. Remember, it's a very important one. When I becomes very large value, the ratio of the coefficient ai plus 2 and ai, okay, becomes equal to 2 by I. Listen. This is very, very important. I'll take the function, say e power plus q square. I'll take arbitrarily, I'll take some function e power q square. What is the expansion of e power q square? 1 plus x square. X square means q power 4, x square by 2 factorial. Then x cube, q power 6 by 3 factorial. Then x power 4, that is q power 8 by 4 factorial. Okay, in a similar manner I can write q power n as n by 2 factorial, because if I have q power 4, I have 2 factorial here. For q power 6 we have 3 factorial. For q power 8 we have 4 factorial. Similarly, for q power n I can write n by 2 factorial. Okay, in a similar manner I can also write q power n plus 2 as n plus 2 by 2 factorial. What does this indicate? The coefficient of q power n plus 2, that is an plus 2, coefficient of q power n plus 2 can be written as an plus 2. An plus 2 is this, is what here? The coefficient of an plus 2 is, the coefficient of q power n plus 2 is written as an plus 2 equal to 1 by n plus 2 by 2 factorial. Okay, or you can also write this as 1 by n by 2 plus 1 factorial. Let me keep it as such. What's the coefficient of q power n? Coefficient of q power n is, it can be written as an. Let me write here. So an equal to 1 by n by 2 factorial. Now I will take the ratio of these two. An plus 2 by an plus 2 by an equal to an plus 2 coefficient is 1 by n by 2 plus 1 factorial, and an coefficient is 1 by n by 2 factorial. So if I divide this by this, n by 2 factorial will go to the numerator. So I will get n by 2 factorial divided by n by 2 plus 1 factorial. Okay, let me keep the numerator as such, n by 2 factorial. This n by 2 plus 1 factorial can be written as, suppose if this is n, the whole term is n factorial can be written as n into n minus 1 factorial. So n by 2 plus 1 into n by 2 plus 1 minus 1, plus 1 minus 1 cancel, so I'll get n by 2 factorial. Okay, so you can cancel these two, therefore I'll get 1 by n by 2 plus 1, or we can also write this as 2 by n plus 2. Okay, you take LCM here, you get n plus 2 by 2, bring the 2 to the numerator. Right, when n approaches large value, this will become equal to 2 by n as n approaches large. Listen carefully. See, the coefficient, the ratio of the coefficient an plus 2 by an when n approaches large is equal to 2 by n. Similarly, for our function, okay, the recursion relation shows that ai plus 2 by ai, okay, when I approaches large, that also become equal to 2 by I. So here 2 by I, right? That means when I approaches large, okay, our function will behave like e power q square. Okay, so it shows that, okay, so from the recursion relation, it is very clear that when I approaches large value, when I approaches large value, okay, the function, right, the function h behaves like e power plus q square. Is it acceptable? Let me check. See, you know the complete solution is psi equal to e power minus q square by 2 into h. Now h is having this form. So if I substitute here e power minus q square by 2 into, in the place of h, I'll put this e power plus q square. If you multiply these two, adding power will give me plus q square by 2. I have plus q square by 2 in the power. You know very well, when q approaches plus infinity or minus infinity, the wave function must vanish. But here, the wave function, okay, since we have positive e power plus q square by 2 here, the wave function will approach infinity. So the function diverges. The function diverges. Okay, that means this is not acceptable. Okay, so what's the inference we get here is we should not allow I value to approach large, because if I approaches large value, your function starts to behave like e power q square by 2, which is not acceptable. Okay, so we should not allow the function to approach very large value. So we have to cut the function, right, after a certain coefficient. Okay, so we have to terminate. So what I'm trying to say is that we have to convert the power series. Remember, power series is an infinite series. It will go up to infinity. But if we allow the function to go up to infinity, your function starts to behave like this. Okay, which is not acceptable. Therefore, you have to terminate your series after certain value. Okay, so we have to convert the power series into a polynomial. Okay, that is, we have to truncate the series. Okay, yes, how to truncate the series? Right? Yeah, it is very easy. Listen, we have the recursion relation. What is the recursion relation we have? ai plus 2 equal to 2i plus 1 minus lambda by I plus 2 into I plus 1 into ai. This is the recursion relation we have. Okay, suppose if we want to stop the power series after certain value, what we have to do? We have to make the coefficient 0. Okay, so after a particular coefficient ai, I should make the other coefficient 0. How to do that? For this, you have to fix the value of lambda. Suppose I'll take lambda, suppose I'll fix lambda as say 2v plus 1. Suppose I'll take lambda as 2v plus 1, it appears like 2i plus 1. Okay, 2v plus 1, such that v is an integer. V is an integer, it takes value 0, 1, 2, 3, 4, etc. Okay, when I equal to v, right, when I become equal to v, what will happen? If I is equal to v, then 2i plus 1 minus lambda, 2i plus 1 minus lambda automatically becomes 0. Right? So when the value of I and the value of v becomes 0, this numerator becomes 0, automatically this coefficient becomes 0. Okay, say for example, suppose if I have a2, if a4 is 0, automatically a6, a8, everything becomes 0. Okay, so we can terminate, okay, we can truncate the series into a polynomial by making a condition on lambda. So what is the condition? Lambda, I am fixing the lambda as 2v plus 1. Under this condition, where v is integer, under this condition, the power series, okay, becomes or behaves like polynomial after certain value of the coefficients. Right? So this is very important, keep this in mind. Okay, now what I am going to do is that, so lambda value has a certain limit. Okay, now so here listen, from the recursion relation, suppose if I know the value of A0, suppose I know the value of A0. If I know the value of A0, I can find A2, A4, A6, etc. How? See, let me use the recursion relation here. This is the recursion relation we have. Okay. Suppose if I know A0 means I am substituting I as 0. If I put I0, I will get A0 here. Okay. Wherever I is there, you put 0, so I will get A2. So if I know A0, I can find A2. But what is A2? A2 equal to, if I put I0 here, I will get 1 minus lambda by I is 0, so you have 2, here I have 1, so 2 into 1 is 2 into A0. So if I know the value of A0, I can find the value of A2. Similarly, if I know the value of A2, I can find the value of A4. How? Substitute wherever I is there, in the place of I you put 2. So I will get A2 here, right? And I will put I is 2 here and I is 2 here. So 2 plus 2 is 4. I will get the coefficient for A4. What is A4? A4 equal to, if I put I equal to 2 here, 2 into 2, 4, 4 plus 1, 5. So I will get 5 minus lambda by I value is 2. So 2 plus 2, 4. Here 2 plus 1, 3. 4 into 3, 12. 12 into A0, 12 into A2. And we know the value of A2 here. So if I substitute, I will get 5 minus lambda into 1 minus lambda by 12 into 2, 12 into 2 into A0. Okay, so in a similar manner, if I know the value of A0, I can find A2, A4, A6, A8, and I can also write these even coefficients in terms of A0. Right? Yeah, in a similar manner, if I know the value of A1, suppose, if I know the value of A1, I can find A3. What is A3? In the recursion relation, wherever I is there, you put 1. So if I put 1 here, I'll get 2 into 1, 2 plus 1, 3. So I'll get 3 minus lambda by, if I put I equal to 1 here, I'll get 3. Here I'll get 2, 3 into 2, 6 into A1. Okay, if I know A3, I can find A5. How? Wherever I, in the place of I, you put 3 here. So I'll get, okay, in the place of I, I'll put 3. So if I put 3 here, so I'll get 3 into 2, 6, 6 plus 1, 7. So I'll get 7 minus lambda by, if I put 3 here, 3 plus 2, 5, 3 plus 1, 4, 4 into 5, 20. Okay, so this is the relation, right? And we know the value of A3 here. If I substitute A3 here, I'll get 7 minus lambda into 3 minus lambda by 20 into 6 is 20. 20 into 6 into A1. So if I know the value of A1, I can find the coefficient A3, A5, A7, A9, etc., etc. And I can also write these coefficients A3, A5, A7 in terms of A1. Okay, so from this, it is very clear that this equation or the function h of u can be written in two parts. One consists of even coefficients. One function consists of even coefficients. The other function consists of odd coefficients. Okay, you can divide this function into two parts. This even coefficients, right? You can all write even coefficient in terms of A0. So I can write A0. I can take A0 as common. So A0 into 1 plus the first coefficient 1 plus 1 minus lambda over 2 plus 5 minus lambda into 1 minus lambda by 12 into 2 is 24 plus etc. etc. Similarly, the odd coefficient, they have A1 as common, so you can take A1 common and you can also write this as 1 plus 3 minus lambda over 6 plus this term, that is 7 minus lambda into 3 minus lambda by 20 into 6 is 120 into etc. etc. So we can write this h in two parts. Okay, one is one function consists of odd even coefficient, the other function consists of odd coefficients. Listen, in the actual solution, right, either this part will survive or this part will survive. Right, it depends upon the value of v. Suppose if I choose v as even value, then automatically this odd function, okay, should be taken as 0. Or should be considered as, otherwise the function will become like a polynomial, power series. I don't want the function to behave like power series. We want the function to behave like polynomial. Okay, so what I am trying to say that suppose if v is even number, right? You know very well, lambda equal to, we have fixed lambda as 2v plus 1. If v is even number, if v is even, then we should keep a1 as 0, right? Because if I keep v1 even, then only this part survive, and we should cancel this part. Otherwise, your function will become like the power series. Therefore, to cancel this, I should keep a1 as 0. Is it clear? Yeah. Similarly, if v is odd, suppose I choose v as odd. If I choose v value as odd, then this part will survive, and we should make this part 0. To make it 0, I should keep a0 as 0. Okay, I should keep a0 as 0. How to do that? Yeah, sorry, I'm supposed to keep a0 as 0. So remember, this is very important. Okay, either the odd solution will remain, okay, or the even solution will remain depending upon the value of v. Okay, yeah, this is very, very important. Keep this in mind. Okay, suppose let me show you. Suppose I'll take say v equal to 0. If v equal to 0, what's the value of lambda? If v is 0, lambda is 1. If I put lambda as 1, see the recursion relation. In the recursion relation, first let me take I as 0. If I take I as 0, I'll get the coefficient a0 in the right hand side. In the left hand side, we get the coefficient a2. Now we have the coefficient a0. Whether a2 will survive or not, let me check it. How? You know very well, a2 is equal to, I have it here. Yes, it's here. See, a2 equal to 1 minus lambda by 2 into a0. And what is the value of lambda? Lambda value is 1. Lambda value is 1. So 1 minus 1 by 2 into a0. So automatically 1 minus 1 becomes 0. So a2 will become 0. That means only a0 will survive. a2, if a2 is 0, automatically a4, a6, a8, all even coefficient, right? Other than a0, all other even coefficient becomes 0. So your function h will behave like a0. Your function is a constant, which is equal to a0. Okay, because a2, a4, a6 are 0. And I told you, if v is 0, v is 0 is even number. If v is 0, you should make a1 as 0. For all v even number of v, we should keep a1 0. Okay, therefore you can write the complete solution as psi equal to, psi consists of e power minus q square by 2 term, and the h term, now the h term is a0. So this is the solution when v equal to 0. Okay, when v is 0, this is the solution, right? If you normalize this, you will get the expression for a0, and you will get the proper wave function for the psi naught. Okay, similarly, if I take v equal to 1, v equal to 1 means odd value. For odd value, I have told you, when v equal to 1, what's the value of lambda? Lambda equal to 3, and we should keep a0 as 0. Whenever you choose v odd, you should keep a0 value 0. Okay, so if v equal to 1, lambda is 3, right? Then I'll get, see, when v equal to 1, what are the coefficients will survive? So let me take I equal to 1 first. If I is 1, then I'll get the coefficient A1 in the right hand side, and the left hand side I'll get A3. Now listen, we know the value of A1, okay, whether A3 survive or not. How to do that? See the recursion relation, A3 equal to 3 minus lambda by 6 by A1. And what's the value of lambda? Lambda is 3 here. Lambda is 3. So 3 minus 3 by 6, it becomes 0. That means only A1 survives, A3 becomes 0. If A3 is 0, automatically A5, A7, A9, correct? All the odd coefficients except A1 become 0. So now your wave function, the complete solution is e power minus q square by 2. And what's the value of h? H is equal to, only A1 survive, so h is equal to, let me write here, that is h, e power minus q square by 2. And what is expansion of h? H is equal to, since A0 is, we have fixed A0 as 0, so only A1 will survive, so A1 into q. A1 into q. Okay, so this is the wave function for v equal to 1. Let me write that at psi 1. Okay, when v equal to 1, this is the wave function. If we normalize this, you will get the exact form of A1, and you will get the complete wave function for psi 1. So in this way, you can find out the wave function for all the levels, right, depending upon the value of v. Okay, so this is very, very important to keep this in mind. Now see, every time by substituting the value of v and finding lambda and finding the coefficient, right, you need not do that. Okay, we actually have a Rodriguez formula to find the nature of the function h. Okay, see, this function h of q is actually called as Hermite. Initially we have taken this as a power series, then we have converted the power series into polynomial, and this polynomial is called Hermite polynomial. Hermite polynomial. Okay, and this Hermite polynomial can be given as h of q equal to minus 1 power q hv of q minus 1 power v into d power v by dq power v, okay, into I have one more term here, e power minus q square by 2. Okay, so minus 1 power v into dv power dq, d power v by dq power v into e power q square is the term we have. Okay, so this is the Hermite polynomial, general formula for Hermite polynomial. So you can also check it whether this formula is actually we have one more term. Let me write here. Let me write it clearly. The Hermite polynomial hv of q, depending upon the value of v, you'll get a characteristic value for the function h of v. Okay, now what is the Hermite polynomial? Listen, I told you, instead of finding the Hermite polynomial for each value of v by finding lambda and by finding the coefficients, everything, okay, you can directly substitute the value of v, and you can find the value of the Hermite polynomial by using this function, Rodriguez formula. Let me give the Rodriguez formula now. The Rodriguez formula says that, yeah, hv of q is minus 1 power v into e power q square into differential d power v by dq power v into e power minus q square. Okay, so this is the general formula for Hermite polynomial. general formula. Right? If you substitute V0 or V1, V2, V3, you will get directly the nature of the polynomial. Okay? Yeah. So keep this formula in mind. This is very, very important. Okay. Now, so if I put V equal to 0, so what is H naught of Q? When V equal to 0, when E equal to 0, the Hermite polynomial value is, if I put 0 here, minus 1 power 0 is 1. We have e power q square. D power 0, dq power 0 become 1. So we have e power minus q square and e power plus q square here. If I multiply, I'll get e power 0, e power 0 is 1. So the Hermite polynomial value for v equal to 0 is 1. Similarly, when v equal to 1, right, put 1 here, so I'll get minus 1. So h1 of q equal to, when v is 1, I'll get minus 1 here, and we have e power q square. I'll get d power by dq, d power 1 by dq power 1, so d by dq of e power minus q square. So this on differentiation will give e minus 1 into e power q square. If I differentiate this, I'll get e power minus q square to minus 2q. So minus of minus will become plus, so I'll get 2q into this become 1, so you'll get 2q. So the Hermite polynomial for v equal to 1 is 2q. In this manner, you can find the Hermite polynomial for all the values of v. Okay, whether it is odd value or even value, you can find using that. Okay, yeah. So this is regarding the wave function, right? So the complete wave function is for one-dimensional simple harmonic oscillator. The complete wave function psi, which depends on the value of v, and it varies with the coordinate x. Okay, can be given as hv of x equal to, we have a normalization constant actually. Let me write the normalization constant, but before that I like to give one more information, that is about energy, because these v values, okay, fix the energy levels. Okay, if v equal to 0 corresponds to the ground state energy, and v equal to 1 corresponds to the first excited state energy. Okay, so in this way you can find the solutions, you can find the energy states. Okay, so the complete wave function, let me write it as a normalization constant which depends upon the value of v into the Hermite polynomial hv of q and the asymptotic solution e power minus q square by 2. This is the complete solution. And what is the normalization constant? Normalization constant nv, we can get this by normalizing the wave function. Okay, let me show that in the next lecture. Here I'll just give you the formula. Nv equal to square root of Nv equal to alpha by pi whole power 1 by 4, okay, divided by square root of 2 power v into v factorial. This is the formula for the normalization constant, and I have already given the formula for hv of q. Okay, so after finding the normalization constant for a given value of v and Hermite polynomial for the given value of v, if you substitute all these things here, you will get the complete wave function. So this is the formula for complete wave function for one-dimensional simple harmonic oscillator. Okay, yeah. So in the next lecture, I'll show you how to find the value of nv. Before completing the today's lecture, let me give this point. See, we have fixed lambda value as 2v plus 1. Okay, and we know very well what is lambda. Lambda is equal to, in the last lecture I showed this, lambda is equal to beta by alpha. Okay, what is beta? Beta is nothing but 2 mu e by h bar square. Okay, and what is alpha? Alpha is nothing but root of k into mu by h bar square. Okay, so this can be written as 2 mu E by h bar square into, if I bring it to the numerator, h bar square is h bar, we have root of k into mu. You can cancel this h bar and h bar square here. So we got this solution for lambda with this value for lambda. I'll substitute this value here. So what is lambda? Lambda equal to 2 mu E, okay, by h bar into square root of k into mu equal to 2v plus 1. Remember, v is an integer which can take value 0, 1, 2, 3, 4, etc. And this is called vibrational quantum number. It is a quantum number and called vibrational quantum number. Okay, v is the vibrational quantum number which can take value 0, 1, 2, 3, etc. Now, what is root of k mu? Okay, or I'll do one thing. I'll bring this down to the right hand side. So I'll keep E alone here. So 2v plus 1 into h bar root of k mu by 2 into mu. Okay, so this can also be written as, let me write the next page. Yeah, this can also be written as E equal to, okay, I'll keep this 2v plus 1 as such, h bar as such, this 2 as such. This can be combined as, if I write like this, if I bring this mu inside the square root, it will become mu square. Okay, mu square cancel. So I'll get root of k by mu. You know very well, root of k by mu is nothing but angular frequency. So 2v plus 1 into h bar by 2 into omega. Omega is angular frequency. You can convert angular frequency, or you can also write this as, if I bring this, if I multiply by, if I divide by 2 here and here, I'll get v plus half into h bar into omega. Okay, this is the expression for energy. Listen, h and omega are constants. H is a constant, omega is a constant for a given molecule. Therefore, the only variable here is v. And v can take value 0, 1, 2, 3, 4, etc. Okay, we cannot take all possible values. V values are fixed here. Since V values are fixed values, we can take only certain allowed values. Energy can also take only certain allowed values. Okay, so energy is quantized. EV is quantized. That is the point I like to make here. And you can also write this expression as EV equal to V plus half into, what is h bar? H bar is h by 2 pi. And what is angular frequency? Angular frequency is 2 pi into linear frequency nu. 2 pi cancel. So you can also write this as EV equal to, this is V plus half into h nu. This is the expression for energy or vibrational energy of a one-dimensional simple harmonic oscillator. Okay, yeah. So depending upon the value of V, this energy gets different possible values. Right? We'll discuss about this energy and wave function in the next lecture. Okay, I stop here. Thank you for listening.